Hey everyone, let's continue our study of series, and what you'll see for the next few lectures is each day we're going to learn a new test, maybe two tests, that allow us to deal with different types of series until in the end we're going to have a fairly substantial list of tests to allow us to handle various types of series. So let's get started. Let's start off with a sequence. So let's let A sub n be a sequence. And we do require all of these numbers to be greater than or equal to 0. So let's say where each A sub n is greater than or equal to 0. What I'd like to do is basically draw a graph. I want to plot these points. So we can plot the sequence as follows. So let me mark some integers here. So 1, 2, 3, 4, 5. That should be enough. 1, 2, 3, 4, 5. So I have my sequence A sub 1, A sub 2, A sub 3, A sub 4, and so on. So for A sub 1, what I'd like to do is above 1, go up to height A1 and put a little dot. And then for A sub 2, go up to height A2 and put a dot. Do the same thing for A sub 3, A sub 4, A sub 5, and in general you can do this all the way down, right, as far out as you like. Okay, so here's sort of a picture of our sequence. Now remember, we're really studying series. And so if I look at the area of that rectangle right now, what is that? Well, the area of this rectangle, let's see, it's got base 1 and height A1. The area of that first rectangle is A sub 1. Same thing if I look at the area of the next rectangle, right? That rectangle has area A sub 2. The next one has area A sub 3, A sub 4, A sub 5, and so on. This should make you think of Riemann sums, right? And so, if you wanted to find the sum of the series, right, by adding up all the terms of that series, you could do that by adding up the areas of all of those rectangles, right? And this is going to go on forever, remember, right? And so, if the sum of the areas of the rectangles converges, right, then the series converges. If the sum of the rectangles diverges, then the series diverges. All right, so now what I want to do is I want to draw a graph that passes through the corners of each of those rectangles. So let's call this just the associated function, by the way, y equals f of x. Right? It's just that's the graph of the associated function. And what you should notice then, if the area under that graph is finite, then the area, or the sum of the areas of those rectangles, is also going to be finite, which tells us then that the series would converge. So what this is going to allow us to do is think in terms of improper integrals. If the corresponding improper integral converges, then the series converges, and conversely, if it diverges, then the series will diverge. Right, so this leads to, well, let's write it like this. So here's what I want you to think, right? That we can correlate the series with an improper integral. And so we can say something like, note, the integral from, well, it doesn't really matter. I'm going to say from 1 to, where do I want to say? Yeah, from 1 to infinity. To infinity. Of the associated function, f of x dx, converges if and only if the sum n equals 1 to infinity of a sub n converges, right? So that's sort of the intuition behind what I'm about to write down. So this theorem is going to be our next test. It's going to essentially say this, although there are some conditions we need to include here. So then this theorem right here has a name. It's called the integral test. And it goes like this. So let's let f of x be continuous, decreasing, greater than or equal to 0, such that f of n is equal to a sub n. So what we have then, this is just saying that we've got the associated function, right, when f of n is equal to a sub n. And the restrictions, the conditions that we need to make all of this work, we need f of x to be continuous, decreasing, and have a graph above the x-axis. Then, the integral, and let me say this a little bit better before I actually write down my conclusion. I don't need it to start right here. It actually can start at any point, right? So that way we can look at series whose starting point is n equals k. So here, let's say this on the interval from k to infinity. Sorry, I just want to extend that, right? So we need to be continuous, decreasing, positive, give the appropriate output on the interval from k to infinity. Then, the series sum n equals k to infinity of a sub n converges if and only if the integral from k to infinity of f of x dx converges. So this allows us to use the theory of improper integrals to study convergence and divergence of infinite series. Now, one thing to notice, when I say if and only if, the way you interpret this theorem, if the improper integral converges, then the series converges. If the improper integral diverges, then the series diverges. In fact, so let me just say that. So usage here. All right, this is the way you want to interpret this statement right here. If the integral from k to infinity f of x dx converges, then the series converges. And if the integral from k to infinity f of x dx diverges, then the series diverges. Right, so this is how we will put our theorem to use. Another thing to notice from the integral test tells us whether it converges or diverges. It does not tell us what it converges or diverges to. Right? All it does is tell us whether it converges or diverges. Okay, but let's see this in action now. So this is one that we looked at last time, and I said, well, we don't have enough technology to show that it converges or diverges yet, but now we do. So the series, so sum n equals 1 to infinity, 1 over n. That's the series that looks like this: 1 plus 1/2 plus 1/3 plus 1/4 plus ... This goes on forever, and this series has a name, so this is called the harmonic series. And what I'm going to do now is I want to use the integral test to actually show that this series diverges. Now, one thing to be aware of All right, so what test do we have so far? We have the geometric series test, we have the test for divergence. Now we have the integral test. We also have telescoping. So this series right here, it's not telescoping, it's not geometric. So all we could use, we could try the test for divergence, we could try the integral test. So first note, limit as n goes to infinity of 1 over n equals 0. That means that the test for divergence tells us nothing. Basically, the test fails, right? So the test for divergence gives no information, right? If the limit was equal to something non-zero, then we could just stop and say, oh, the test for divergence tells us that it diverges. All right, when you get a limit of 0, you get nothing. Okay, so now let's try the integral test. Now remember, so we apply the integral test. So let's see, the integral test tells us that the associated function needs to be decreasing, continuous, and positive. So we have f of x equal to 1 over x. This function is definitely decreasing. It's definitely continuous. I mean, if you think about the graph of 1 over x, right? It's decreasing, it's continuous on 1 to infinity. It also has a graph that's above the x-axis, right? So we can apply the integral test. In general, I'm not overly concerned with checking the conditions of the integral test, but remember, in certain cases, if you apply it to a situation where it's not applicable, then the integral test can give you false information. Okay, so now here's my associated function. I'm going to look at the integral from 1 to infinity, 1 over x dx. That's equal to, so remember, anytime you have an improper integral. Oh, actually, well, yeah, okay, I'll compute it, but here's one thing you should remember. For improper integrals, in fact, I don't even really want to compute this one. Yeah, so, well, let me remind you how to compute one first, but then I'm going to remind you also of a rule. Whenever you have a function 1 over x raised to the p, it is convergent, right? When p is greater than 1, and it is divergent when p is less than or equal to 1. But let me just to remind you how to compute improper integrals. Remember, you first rewrite it as a limit, so this would be limit as t goes to infinity, integral 1 to t, 1 over x dx. That's equal to limit as t goes to infinity, natural log absolute value of x going from 1 to t. That's equal to the limit as t goes to infinity, natural log of t minus the natural log of 1, but the natural log of 1 is just 0. And so what do we get? That's equal to infinity. So the improper integral diverges. So now we write down our conclusion. And remember, anytime when you're studying series, the answer is not just a yes or no. It's an explanation of how you know that it's convergent or divergent. So we say, since the integral from 1 to infinity, 1 over x dx, diverges, so does the harmonic series by the integral test. Right? So a computation plus a concluding sentence is what you need every time when you're studying series, right? When we write up your answer, you want to have a computation followed by a concluding sentence. So let's just say this now more generally. From Math 142, you know this, the integral from, let's say, k to infinity of 1 over x to the p dx converges for p strictly greater than 1 and diverges for p less than or equal to 1. And so what that tells us gives us a new test called the p-test. So for p, you know what? First, let me write down a name. This is called a p-series. A series of the form sum n equals k to infinity 1 over n to the p, right? So if you have 1 over n raised to some constant power p, this has a name, it's called a p-series. And so from this right here, we know exactly which values of p give us a convergent versus divergent p-series. All right, so we can say, so sum n equals k to infinity 1 over n to the p converges when p is strictly greater than 1 and diverges for p less than or equal to 1. Right? So if you get a series like this, so for example, sum n equals 3 to infinity 1 over n to the 2.6, we can just immediately say this one converges. And all we need to do is say, oh, we know that this is a p-series where p is 2.6. That's a number greater than 1, so it converges. Right? And the point is, now, according to the integral test, we know exactly which p-series converge or diverge, so you don't need to reapply the integral test for these. We already know the answer for any p-series. Okay, here's another example. So let's look at this series right here, sum n equals 1 to infinity n squared over n cubed plus 1. So let's just kind of run through our test. This is not telescoping. It's not geometric. The test for divergence would give us no information, right? If I take the limit of that sequence right there, I'm going to get 0. So all we have left is the integral test, and so let's try that. You can check the associated function x squared over x cubed plus 1. It is decreasing, it's greater than or equal to 0, and it's continuous. And so let's look at the integral from 1 to infinity of x squared over x cubed plus 1 dx. So remember, this is an improper integral. We need to rewrite it as a limit. So that's equal to the limit as t goes to infinity, integral 1 to t, x squared over x cubed plus 1 dx. Now this is set up to do substitution. If we let u equal x cubed plus 1, then du is 3x squared dx. And so this is going to give us a limit as t goes to infinity. Let's see, my lower limit is going to be 2. My upper limit will be a t cubed plus 1. Remember, oh, and there's a 1/3 also. 1/3. Remember, whenever you do substitution, you got to change your limits of integration. So this will be 1/3 integral 2 to t cubed plus 1, and then we will have a 1 over u du. Now we can compute the limit. So this is limit, or sorry, compute the antiderivative. So this is the limit. T goes to infinity. 1/3 natural log absolute value of u, and we go from 2 to t cubed plus 1. Now let's plug in the limits of integration, and so this will be a 1/3 times natural log t cubed plus 1 minus natural log of 2. As t goes to infinity, this part definitely goes to infinity, so this is equal to infinity, so it diverges. And so what do we say then? Since the improper integral, right, the integral from 1 to infinity, x squared over x cubed plus 1 dx diverges, so does the series, so sum n equals 1 to infinity, n squared over n cubed plus 1 by the integral test. Now, as I said before, the integral test only tells you whether it converges or diverges. It does not tell you whether, or it does not tell you when it converges. It doesn't tell you what number it converges to, right? So it does not tell you any information about the sum itself. All it tells you is that there is a sum or that it diverges. But if it converges to some number. There is some number s for which that infinite series adds up to. So suppose we have, so let's call it, so let's say s is the sum n equals, I don't want to do k. Yeah, k is fine. To infinity, a sub n is, I want to word that, yeah, is a series for which the integral test applies. So what that means is we've got a convergent series. It converges to some number s that we don't necessarily know who it converges to, but we know it converges, and we are able to show that it converges by the integral test. The nth remainder is, and we write this as r sub n, and by definition it is s minus s sub n, where s sub n is the nth partial sum. So what does the nth remainder measure? It measures the error. S is the actual sum. S sub n is the approximation, right? If you're trying to approximate your series by adding up from a sub k up to a sub capital N, this would give you an approximation, right? We can't go all the way to infinity, so if we stop at s sub n, we just have an approximation of the actual sum. And so the nth remainder measures how close the approximation is to the actual sum. So here's a amazing fact, I guess you could say. So let's call this a theorem. The integral from capital N plus 1 f of x dx, where f of x is the associated function, is less than or equal to r sub n, which is less than or equal to the integral from n to infinity of f of x dx. So what does this do for us? Well, if you have a remainder and the remainder is telling you the error, right? In practice, you'd like to know how good or bad is the error? How close is the approximation to the actual sum? Right? And if you're trying to get a good approximation, then what you want to do is you want to make your remainder small. And so this formula right here, this inequality, tells us how close the remainder is, or how small the remainder is. In particular, I usually focus on the right-hand portion here. It tells us that if you want the remainder to be small, you should find the end value for which this improper integral is small. And if you do that, then you have a good way of approximating the actual sum. So let's do an application. And so I refer to this as the integral test error approximation. Or error bound is really what this is. So application. So for sum n equals 1 to infinity, 1 over n to the fourth. This is a p series where p is greater than 1, so we're guaranteed that it converges, right, to some number s. What I'd like to do is find n so that r sub n is less than 1/1000th, so less than 0.001, and then use this to approximate the actual sum s. All right, well, here's the idea. I would like to find n so that r sub n is less than 1/1000th. According to this inequality right here, if I could make this improper integral less than 1/1000th, that would guarantee me that r sub n is less than 1/1000th. So that's what I'm going to do. I'm going to find n so that the integral from n to infinity, 1 over n to the fourth, x to the fourth, x to the fourth, dx is less than 0.001. If I can do that, then I'm guaranteed that my remainder is less than 0.001. Okay, so let's compute this improper integral here. So we get limit as t goes to infinity, integral from n to t, 1, and let's write this as x to the minus 4 dx. Compute the antiderivative, so now we've got limit as t goes to infinity, x to the minus 3 divided by minus 3, and we evaluate from n to t. That's equal to the limit as t goes to infinity. So this will be, when I plug in the upper limit, I'm going to get negative 1 over 3t cubed. When I plug in the lower limit, we will get plus 1 over 3n cubed. As t goes to infinity, this part right there is approaching 0, and so what we're left with is 1 over 3n cubed. So what I want then is I need the n value. So we need n so that 1 over 3n cubed strictly less than 0.001, which is 1 over 1000. And then if we want to solve this inequality, that means that I need n cubed to be greater than 1000 over 3, which is about Oh, so okay, so if I take the cube root, we need n greater than 1,000 over 3 cube root. This is about 6.93. So I need n to be an integer greater than 6.93, so let's choose n equal to 7. Okay, now s sub 7 what does that mean? So s sub 7, that's going to be the sum, n equals 1, and don't go to infinity now, we stop at 7, 1 over n to the 4th. Right, so what does that mean? It means 1 plus 1 over 2 to the 4th, plus 1 over 3 to the 4th, plus 1 over 4 to the 4th, plus 1 over 5 to the 4th, plus 1 over 6 to the 4th, plus 1 over 7 to the 4th. And if you add all this together, what you get is 1.02295. Right, so there is s sub 7. Right, if you add the first 7 terms together, that's what you get. And now what we know is that the actual sum, so sum n equals 1 to infinity, 1 over n to the 4th, is approximately equal to 1.02295. Right? It's not exact, it's just approximation because we're not adding all of the terms, we're only adding the first 7. But we know that the actual sum is within 1/1000th of that right there. So I think this is a pretty amazing theorem. It's pretty fun, and what this tells us is you can add all the way to infinity, right, to get the exact answer, but we don't have time to do that. And if you want a good approximation, using this integral test approximation process allows us to get an error or get an approximation to within whatever tolerance you like, right, by choosing n large enough. Right? Our approximation will get better and better and better. So that's the idea. If you want a better approximation, you just choose n to be larger. Okay, that's a good place to stop, so we'll see you next time.